turbine generated synchronous inductance. The rotor features different magnetic reluctance along its D and Q axis. As a result, the inductance of the stator winding depends on the rotor position. The maximum value you will get if the rotor D axis is aligned with the stator magnetic field. This inductance value is referred to as the synchronous inductance. My task is to calculate the maximum and the minimum inductance values. I am going to repeat the real case experiment. I will energize only the single phase, for example AX. I will put the rotor in different positions and calculate the inductance. In real case experiments, they used AC current. They measured the voltage, the current, and the phase shift between the current and the voltage. But in my case, with the help of QuickField, I can look inside and see the magnetic field distribution. So there is no need to use the AC current. I will use DC current and measure the magnetic field energy. And the inductance is the ratio of the magnetic field energy value doubled to the electric current value squared. Okay, let's start QuickField now. In QuickField, I create new problem, generator. Next. Problem type is magnetostatics, length units are millimeters, model class is plane parallel, and the axial length of the generator is 5400 millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD DXF file. Here is the file, and I will import it. The model is imported. You can recognize rotor, air gap, stator. Let's assign labels. Through labels, you can explain the geometric object's meaning and provide physical properties. Well, let's zoom in. My task is to calculate the inductance of the stator winding. There will be no currents in the field winding on the rotor, so I can select everything and assign label air. So this would be the rotor, this would be the stator yoke, and these blocks will be the stator teeth. To select multiple objects at the same time, hold the control button pressed. Now these blocks are teeth. And I need to assign label to the phase winding. There are 10 conductors at the bottom of the slot. This is A. And there are 10 conductors at the top of the slot. Okay, this is A. And on the other side, there will be conductors with the opposite direction of the current. 10 conductors in the bottom of the slot. This would be X. And 10 conductors at the top of the slot. X. Other phases are not energized, so I will leave label A for them. Now let's also assign the label to the external boundary. Again, hold the Ctrl button pressed to select multiple objects. External. Now let's provide physical properties for these labels. Double-click the label name in the tree. The permeability of the air is 1. For the rotor, I should specify the BH curve data. I already have the data prepared here in the file, so I simply select, copy, and paste the BH curve data here. Okay, close. For the yoke, again, I should specify the BH curve data. This is the BH curve data for the yoke. Copy, paste it here. Close, okay. And for the T, I should specify again the BH curve data for the T. These are the data. Copy, paste it here. Close, okay. Now to be able to calculate the inductance of the phase winding, I should supply some electric current in this winding. For example, for the phase A, which is made of copper, I specify the total current of 100 amperes. The individual conductors are connected in series. And the return current will flow in the phase X, which again made of copper with the permeability of 1, and the total current is minus 100 amperes. Again, the conductors are connected in series. The magnetic field is contained within the electrical machine. There is no magnetic flux going outside the stator. So for the external boundary, I specify 0 magnetic potential. Now the geometry model and the data are ready. Before I can run the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. The problem is solved. Let's take a look at the results. Here you can see the magnetic field lines. You see the rotor axis is not aligned with the stator magnetic field. Let's calculate the inductance. I'm going to use the inductance wizard built in QuickField. First, I will calculate the stored energy. Next, I will specify the current that generated this magnetic field. And this is the inductance, 0.017 Henry. This is the inductance of the electrical machine that has the length of 5,400 millimeters. Okay, what will be the inductance value if we will rotate the rotor? Let's find this out. I'm going to use the label mover parametric analysis tool. First, I need to specify the base problem, generator PBM. Next, I should specify the values to measure. I'm going to measure the stored magnetic field energy. Add values, add compound contour, and add all blocks to the contour. Okay, for all these blocks I'm going to measure the magnetic field energy. Close. And next I should specify what I'm going to change. Record steps. I'm going to rotate the rotor by 10 degrees. Add step. You see the new problem was created, and in this problem the rotor is rotated by 10 degrees. And I'm going to repeat this step 9 times. Okay. Now everything is ready. I have the base problem specified, I have specified the values to measure, and I have specified the steps to perform. We can get the results now. You see, a set of problems is generated, and in each problem the rotor is placed in some specific position. Then these problems will be simulated, and in each problem the stored magnetic field energy will be calculated. And the results will be stored here in the table. On computers with multi-threaded processor, labelware can simulate several problems simultaneously, which is much faster than solving problems one by one. You see the processor was occupied by 100% and the memory as well. And now for each of the solved problems, the stored magnetic field energy is calculated. And now the last problem will be simulated. Here you can see the results, how the magnetic field energy depends on the rotor position. Let's take a look at the plot. This point corresponds to the maximum value of the inductance, of the synchronous inductance, when the rotor axis is aligned with the stator magnetic field. Let's take a look at the field distribution. Here it is, and this point corresponds to the minimum value of the inductance when the rotor axis is perpendicular to the stator magnetic field. Here it is, this is the stator magnetic field direction, and this is the rotor d-axis. Now let me show you how to calculate the inductance from these values. For example, I will take this magnetic field energy value. To calculate the inductance, I should double this value and divide by the electric current value squared. Remember, I have specified the current value to be 100 ampere, so divided by the 100 and divided by the 100 again. And here is the inductance value, 0.017 Henry. If you search for the turbine generator synchronous inductance on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result, pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.